simple machines. Here we go. Okay. What do people know about simple machines? Is it still blinking red? I know, we've been having some problems. Here we go. Okay. So what do people know about simple machines? Ethan?
That they're machines that make work easier.
So they make work easier. Mira?
There's 6 different kinds of machines.
6 different kinds. Andrew?
Each does a different job.
Good job, Melissa. Is your hand up?
Yes.
Yep, go ahead.
They're used everywhere.
Used everywhere. Trey?
They need like someone or some they need someone to power it.
Now you said power.
Like make it work. Make it work.
So what did they call that in the lever reading we just did? I think we just read that. Angus, do you know?
Yes.
We need a force. A force to work. Does anybody remember the formula for this, out of curiosity? Sam?
Force times distance equals work.
Yeah, equals work. And are we talking about going to our job for work?
No.
No, what kind of work are we talking about? John Paul?
Like where you have to do physical work.
Yeah. Does anybody remember what we talked about in order for it to be work? Because I know we had talked about that boulder. Rachel, do you remember? Yes, so even if you try to pick it up and you're sweating your brains out and it doesn't budge, are you actually doing work?
No.
No. So I know we've talked about inclined planes, wedges, pulleys the last couple of days. Today we started talking about levers. And what is important about a lever? What does it have to have? What does it have to have? What does it have to have? Noah?
It has to have a bar that turns or pivots around a fixed point.
Nice job going back into the story. Charlie?
Does it also need fulcrum?
It has that fulcrum. And if you take a look, how many different types of levers are there? How many different types of levers? Thomas?
6.
Take a look at the book. That's how many simple machines there are. How many types of levers are there?
3.
3. First class, second class, third class. And I know that when we looked at them, John Paul, what did you ask?
I asked what was the difference between the first class lever and the second class lever.
Right, because he saw it had effort, right, resistance, and a fulcrum in the bar. But John Paul, what did we talk about? Why is it different?
That they're in the resistance is in different places.
Yes. Is the effort. What's going on with the effort in the first class lever versus the second class? Does anyone know what can notice that in the picture? Stephen, what's going on? Yeah, so in the first class, which way is the effort going? That might be a better word for it. Which way is the effort going? Bella, look at the first class lever. Which way is the effort pointing to?
Down.
Down. Aiden, what about the second class lever?
The second class lever is pointing, it's going up.
Going up. Where's the fulcrum? Sydney, where's the fulcrum in the first class and the second class lever? Where's that fulcrum? Actually, in all 3 pictures, where's the fulcrum? Where's that fulcrum? In all 3 pictures, where is it? Do you want to call for help? Go ahead.
At the right side?
Would you agree with that, Sydney? Do you see where the fulcrum is? The triangle? Is it on the right side of each of those 3 pictures? Does the fulcrum always have to be on the right side? Amira? No. What happens if you move the fulcrum? What would happen, Ethan?
You'd have to move the effort force and
Yeah.
the resistance
Good, so this morning we talked about simple machines in the playground. The seesaw, where's the fulcrum? Where is it actually? Where's the fulcrum on a seesaw? Where would it be? Amanda, you're thinking about that. I see that. Where do you think it is? Take a risk. In the middle. Where's your force and your resistance? Where is that? Where's your force and your resistance on a seesaw? Ooh, where would it be? Kelsey? On the ends. One person's the force, one person's the resistance. Now, if I got on one side of the seesaw, and I was the effort, and Alec got on the other side, and he was the resistance, what would happen to Alec right away? What would happen? Allison, why? But why would he go up? Is it because I'm the effort? We would actually have to do something to move. What would we have to do? I'd have to apply effort. What would I have to do to make Alec move? I'd have to go up. But why would I be down right away in the beginning and Alec be up? Alec, do you know why you'd be up?
Because you have more weight.
I have more weight. There's more gravity pushing down on me than there is on Alec. So we are going to take a look at levers. And I'm going to ask Rachel Shapiro to shut the light off entirely. Because today's activity, we're going to be making levers. It's a great question if we're going to work on pulleys tomorrow. There you go.
Dear Tim and Moby, we're learning about levers in science and I'm totally confused. Can you explain them? From Carlo. I think Moby just got a taste of levers in action. Levers are pretty simple, really. They allow us to move things more easily by magnifying our efforts. A lever has 4 components. The lever itself is a length of relatively stiff material. The fulcrum is the point on which the lever balances or pivots. The load is the weight or resistance that needs to be overcome. And the effort is the force you apply to the lever. These elements can be rearranged to make 3 kinds of levers. This is a class 1 or first class lever. The fulcrum is positioned between the effort and the load. A seesaw is a good example of a class 1 lever, so is an old-fashioned scale. The thing to remember with levers is that distance and effort are interrelated. If you're willing to increase the distance over which you exert force, then you can decrease that force and still get the job done. It's like the difference between lifting a safe straight up over your head and pushing it up a hill to the same height. The total amount of effort expended is the same in both cases, but pushing it up the hill lets you extend the effort over a longer distance, so you don't have to push as hard. Take a look at this simple class 1 lever. See how the fulcrum is in the middle? Lifting Moby in this case requires a lot of force. You don't have bones. Anyway, this is the distance over which we have to exert force to lift Moby to the top. We can increase this distance by moving the fulcrum towards him. Since the distance is increased, the amount of force needed to lift him is decreased. Let's see some more levers. The fulcrum in a class 2 lever can be found at one end with the effort applied at the other end. The load is somewhere in between. A wheelbarrow is a class 2 lever. Since the load is close to the fulcrum, the effort needed to lift the load is spread out and lifting is easier. In both class 1 and class 2 levers, the effort needed to move the load is smaller than the load, but the effort travels further. Class 3 levers have a fulcrum at one end like a class 2 lever, but in a class 3 lever, the position of the effort and load are reversed. Here, the effort needed to move the load is actually greater than the load itself, but the load moves further than the effort. Tweezers are class 3 levers. So is your arm. Before Moby and I understood levers, playing on a seesaw was about as much fun as waiting for a bus. But if Moby, who weighs about twice as much as me, moves halfway up the seesaw, we can balance with no problem.
do I have to do? According to what you just saw, Noah, what do I have to do? I'm going to have to move closer to the fulcrum. Is the placement of the fulcrum important?
Yes.
I want you to keep that in mind. I'm going to ask my administrative assistants to pass out the science lab sheets, and I'm going to ask you to take out the sheet I put up under the document camera. You have it. You have that? The design process. I think you all have that in your science folder. Does yours match mine? Perfect. I have the color copy. That's the original. Yes. Does yours match mine? Perfect. You can close your books, yeah. Thank you. Did anybody not get one? So does everybody have a packet? The design process. We've been talking about this in Emerging Engineers. We've been talking about this at the Young Inventors Project, and now we're going to be talking about it today. The first thing you do in the design process is what? What is the very first thing you do? Very first thing. But some people have figured it out. More people do. Rachel Conniff? Define a need or problem. We have a problem. You're going to be given a marshmallow bag. One marshmallow. You have to make goes so many inches. Your group decides how many inches it goes, but it cannot go longer than the ruler we give you. So you're going to group is going to have to decide how many inches to move a marshmallow. I'm not telling you how to build it. You have to figure out how to design it. What's the second step in the design process? The second step. Amanda? You have to come up with ideas. How are you going to build your catapult shooter, your lever, to get the marshmallow from the lever to the distance your group decides? You're going to brainstorm. Then what's the third thing you do? Rachel Shapiro.
Select the most promising idea or design.
Yeah, you're going to have to pick the one that you think is the best. The fourth thing you do, what is the fourth thing, Anne-Marie?
Communicate and plan the project.
Communicate and plan. You're going to plan it. The next thing you do, Stephen?
Create, build, create, and test the design.
You're going to build your catapult shooter, and you're going to test it. And the very last part of this, oh, and what's the last step in the design process? It's step 6.
Evaluate, revise, and design.
You might have to make some changes in order to get it to where you need to be. You are going to be assigned a group. There's going to be the inclined planes group, the wedges group, the screws group, the pulleys group, the levers group, and the wheels and axles group. Does that sound familiar, those 6 things?
Yes.
What are they? What are they? John Paul, what are they?
Simple machine.
They're simple machines. Your group is going to be a simple machine group making a simple machine. In each baggie there are identical items. And I have some parents in the room that are going to be around to help us. Are we telling you what to do with these items? Your group has to design a plan to shoot the marshmallow. You're going to be making a design. Now let's take a look at your packet. Please put your name on the top of the packet. If you've somehow misplaced your design paper sheet, I will get you another copy later. However, if you put it back where we tell you to put it, where is it always going to be?
There.
Ooh, Thomas? There, in the science folder. That's what the folder's for. Now the materials list is a little different because when I originally planned this, I planned it with the Cheerios, right? And then I realized that Cheerios, if you step on them, what happens? They break and they crush and it's harder to clean. I changed it, adapted it to marshmallows. The first thing you're going to do is come up with a hypothesis. Who remembers what a hypothesis is? What is a hypothesis in science? Angus, what is it?
What do you think will happen?
What you think will happen. So how can you consistently get, instead of cereal, it's going to be a marshmallow, into a cup? So what do you all know you have in the bag right now? A cup so many inches away. How many of you ever tried to throw a grape in someone's mouth? Be honest. It's kind of like that, except instead of your arm being the lever, what are you actually designing? A real lever, a catapult. So you're going to have to decide how far you want the cup to be, but what's the rule about how far it can be? Rachel Shapiro? Has to be smaller than the ruler. Can you go past your ruler? No. Are we eating the marshmallows?
No.
Just checking. Okay? Has to go into the cup. So you want to get the marshmallow into the cup using the supplies in the bag. So I want you to predict, and if you might be different than your group, is that okay? Could you write your own hypothesis? Good. How can you get it there? What do you think you have to do? Then you're going to design your catapult. You're going to have to discuss how you think with your group how to make this catapult to get the marshmallow into the cup. Anybody have any ideas already in their head? A few of you do. Then you're going to do a couple trials. Why do scientists do more than one trial? Why? Allison, why? They could fail, right? Scientists do fail. We talked about how engineers fail. That's why you have to change. Treya?
There are many trials because you have to scientists, they pick the most promising and best one that works best from every other trial.
Yep.
From the chart.
And what's the part of the lever that's going to help you get the marshmallow into the cup? Rachel? Yeah, what is that called? If you're not sure, you can call for help or you're looking in your book. Good. The fulcrum. So if you notice in your grid, you have the first trial. Andrew, what do I ask you to write about next? Yeah, where did you put that fulcrum? Is it on the left side, the middle, the right side? Where? And then how far did your marshmallow go? How are you going to be able to do the distance? Thomas? You're going to use the ruler we give you. Okay? You have 5 trials. And then it says, if you flip the page, does it say number 2?
Yep.
Explain how you succeeded at hitting the cup. Write about your experiment. And then there are some things to think about at the end. How does placement of the fulcrum affect the experiment? And were there other variables? And who remembers what a variable in science is? I believe the Museum of Science guy that was here the other day talked about variables in his explanation of simple machines. I know we know that a variable in math is a letter that stands for something, but what did he say a variable in science was? Stephen, do you remember what he said?
It was it takes up a word, W equals F times.
That's an example of a variable, but he was talking about a variable in a science experiment. You're talking about a letter being a variable, and that's more math related. Ethan?
It's a number, symbol, or letter that is representing any sort of concept or word.
That's still a variable in math terms. I'm looking for it in science terms. How many of you have no idea what a variable in science is? Should we look it up?
Yeah.
Okay?
Isn't there a glossary here?
I don't think it would be in your book, because we're talking about a science experiment. And I know Shreya and I were going back and forth on Google Docs last night. And Shreya, what did I say is really important when you're searching in Google? What's the most important thing? Do you remember? Because you said you were looking up something, and then I told you something totally different. If you're not sure, you can call for help. Someone may know.
So you have to search what you're actually want to look for.
Yeah, so it's really important to use what? Thomas, do you remember?
As small as word as you can.
The smallest keywords as you can. All right, so let's see if this will help us. and we're going to get cracking on our experiment. It's important to understand what variables are. Yeah, you might want to check it out. What do we find we're often waiting for? To load. Here we go. All right. So scientists use an experiment to search for cause and effect relationships in nature. There's things that change that are called a variable. A variable is any factor, trait, or condition that can exist in different amounts or types. An experiment usually has 3 different types of variables. To me, a variable is something that affects your experiment in science. So it might be, where did you put the fulcrum? Where was your resistance? Where was your effort? The types of tools you used. How do things respond to a certain change? So what's one of the biggest variables that you are going to be working with today? Melissa? What's really going to affect your experiment when you go to build your catapult? But which variable? Which variable is so important today when you build that catapult? What's the most important thing? Turn around and talk to your neighbor. What do you think is the most important thing? I hear it, but yet not a lot of hands were up. Mom, come back. Were there a lot of hands up? But did you hear the same word? I did too. Oh, much more hands up. Melissa? Where the fulcrum is. So what I'm going to do now is show you your groups. We're going to tell you where to go. Rachel Shapiro, could you kindly put the lights back on? The lever group is heading to the reading corner. You're going to have to go this way, because there's another group that's going to be in the reading corner. You can push the chairs out. You can take your bag and your ruler and head over there. The pulley group is also heading to the reading corner. The inclined plane group is heading right here in this space. The screw group is right here in this space. The wedges group is here. Heel stencil is in the back. Take a look at what's in your bag.
Okay, good. I wanted Ethan to be in my room.
I'm going to get everything.
Kelsey, there's a lot of...
Or you guys. Okay.
Sorry.
I mean, you're not actually using the name of your group. You're all designing the same thing, but will each group have the same exact catapult shooter? I just named the groups after simple machines. So if you're in the wedges group, you're not actually making a wedge. What do you got in the bag?
Did you Wait,
this is what you're measuring with. So the ruler's not part of your design. The ruler is not part of your design.
Okay, let's
So what do you think you're going to start with? What do you need to figure out?
how far we get the marshmallow thing.
Yeah?
So when you think about it, alright, so this would be you think about how much so it has to be 100. So
decide where you want the cup, right? So how many inches do you want it to go?
We need to see how big our catapult will be. Yeah, because if it's bigger, we might have to move it back more, but if it's smaller, we have to move it back.
Now, why do you say that?
Because if it's smaller, so the marshmallow might it's bigger. Like this. If it was bigger, we would have more force to put on it, so it would go farther. And since it's smaller, we would have less force to put on it. Let me try.
This is all you need.
Make sure your groups fill out your hypothesis. Your design. Do we tell you what to do with the materials beyond how to use the ruler and the marshmallow has to get into the cup? But you know, Melissa, once you break the spoon, you've broken the spoon. So that's your group's choice.
We have to design it. Are we going to use the spoon to like catapult? Yeah, but how is it stack up the sticks.
So it's your prediction, your guess, like Rachel just said. So how can you consistently get the marshmallow into the cup? What do you need to do in order to get it to fling in? John Paul? So what is going to consistently make it though? What is the most important thing? What do you think? The fulcrum. So you might want to think about the fulcrum, Rachel, because you happen to figure out that the fulcrum was important, right? So what's important about the fulcrum? What does the fulcrum need? What do you mean by balance? Oh. So what's your fulcrum in this creation? Show me where your fulcrum is. What's the actual fulcrum? That, right? So it could be. It depends on what your group wants to do. You might have to play around with it. Ever done this?
How can we make it go better?
What do you think? What's your hypothesis?
We can add a pencil to it.
Alright. You stuck with something?
Yeah.
You might want to use the space by the door for your experiment, by the way. Yeah, you. Because why would I suggest the door over in that area?
Because we have more space.
You have more space. Yeah, Bella.
All the objects.
Did we tell you had to use all the objects?
Nope.
I don't know, Sam, what are you doing? Did you tell him? Why are you raising the fulcrum?
So what is the variable now?
Yeah, let's do like that. We have to make a bigger bed. To be sure. We have to be 100% full.
You okay?
Sam.
Are you okay?
Hold this way, hold the cup. Oh, of course. Okay, can I just see?
Oh, you were just close. Now, why did you decide to design it like that?
Because then,
Miss Freeman,
Could you wait 1 second?
just
Thank you.
to rest it,
Yep.
just launch it.
When you say So what's going on here?
So that's the way we can position the fulcrum.
Oh, so you've made a slidable fulcrum.
Yeah.
Interesting. Yes, Angus. Was there not 6 by, there should have been 6, did your group not get one?
Yeah, we have.
They're by the toilet.
Can we make like a slingshot kind of thing?
Did anybody tell you how to make it?
We could make whatever we want.
You have to make, it has to be a catapult.
Alright, ready?
What does it say on the top of
A catapult.
Any more questions about that?
Has to have a fulcrum.
But we didn't tell you how to make the catapult.
But it has to have
What simple machine do you know you're making?
a lever.
A lever.
See?
Does a slingshot have a fulcrum?
No.
Think about. Alright, Thomas, Angus, do you really need another ruler? Do we have everything we need now?
Yeah, and then Rachel's mom gave me the ruler.
Okay, what's going on with the hypothesis? Oh, you're still working? Yeah, what are you thinking, Andrew?
I was thinking that we would take these and we would like try like so my
Okay.
intention that we would take this spoon and we would put it on there like like we would keep it up.
Okay. What do you think, Amira, about that?
Yeah, I don't see how that's going to work.
So why don't you think it's going to work? What do you think would need to be
Because if he's
adjusted?
putting the sticks in the triangle and the spoon on there, how is he going to launch it if he's going to stick elastic?
Ask him.
Well, what I was thinking is that we would put it like near here.
Okay.
So when we all like tip, that would make it like launch up and fly off. Like it's like going to be like that.
What do you think?
Well, I haven't seen it yet, so I don't know how he's going to put the elastics on or where he's going to put it.
Yeah, it's gonna work.
Start working on it and then adapt it and change it as you go. You think that'll work? But everybody's got to have their hypothesis filled out. And I see 2 blank hypotheses. I don't know. Where's your sheet? Okay, good. Is your hypothesis filled out?
Not yet.
Not yet. Did we all fill out? Yes, but did we fill out our hypothesis before we even started?
Seeing how big it was.
You gotta do your, did you do your predictions first? So we should probably stop.
It went in the cup.
I'm glad you got it in the cup.
You made it go into the cup.
But before you even started, what were you supposed to do? Yep, and it says, how do you think you can get it in the cup? You were supposed to make a prediction. So think about what your group talked about before you did what you did. That's what will go there.
By making so much
Yeah, Andrew.
So like and the last goes together. And we talked about how the brands were supposed to stick to the marshmallow.
So what could you do to change what he said? What I'm hearing from your members is they want to start with that, but there's got to be something that needs to be changed. That's what your group has to figure out. What has to be changed?
Make the fulcrum closer to this, like that.
How's it going over here?
We tried using the pencil.
So what did you try first?
We had it like this, and we tried doing that, and it only went this far.
And why do you think that is?
Because like it's so much on that side, there's not that much room that it can't really launch that far. Then we tried it in the middle, and it went 19 inches. And then we tried it all the way to here, and it went 27 inches.
Have you been able to get in the cup yet?
No, we haven't got it past 30 inches, let alone 36.
So what do you think you need to do?
Maybe we move the food. Yeah, this thing down here. That's a good idea. And then then we have more room. It's just that now we actually need the rubber bands. So can I have the rubber band, please?
problem applying the rubber band now?
Because then we need to stick in place, and it wasn't before, so. Try putting it on the spoon. Oh yeah. Yeah, if we put it like there.
Okay, so now we know this is perfect.
Wait, what's perfect? What's perfect?
This is almost perfect. It has much strength. It has accuracy, but it's a little high.
So have you been writing down your trials as to where you're putting down your fulcrum and then how far it's going? You should probably start doing that.
Yeah, I agree.
I'm glad you agree.
Oh, this is your best. So we found a good place to put it.
So what did you figure out, Bella?
Well, that if you take the popsicle sticks and you put this in between it,
Yeah.
and you could change where to place it. So then if you fling it, the marshmallow. So on the end of the spoon. Near end of the spoon.
All right, so your fulcrum right now is near the end of spoon.
Yeah. Just like one of the together.
Yep.
End of spoon. Stable. No. Remember our first trial? It was in the middle of the spoon. Yeah.
So why don't you put it back in the middle and recreate the trial? See what happens.
I didn't do anything yet. Wait, no. Okay, so that's recreated. So, in the middle, right? Okay, wait.
And they're well on their way. And Ethan, is that working now?
We haven't figured out. We need to. We're trying to make it fulcrum.
We're trying to pencil it.
And so this one's gonna be left side here.
What is that? You used the bag?
Yeah.
Why did you use the bag?
Because the fulcrum, if we use like a stick, then the fulcrum wouldn't work, and the sticks aren't thick enough to do it. Yeah, we folded the bag.
So can you show me how it works?
Yeah. I can't do it because I
know, we got some peekers. I didn't say they couldn't use the bag.
No, they're gonna go
ahead.
They're gonna
Well, where are you supposed to be? If you're here, you're not
They're
supposed
gonna
to.
copy us now.
Go ahead.
Okay, that was a bad. Yeah, fulcrum. Okay, Amanda. Trying to figure out. Do you want me to aiming system? Yeah.
What do you mean an aiming system? Whoa. What do you mean an aiming
These are
system?
like length and how far it's gonna go at the same time.
All right. And if they go under the door, don't worry about it. We'll clean it up at the end. Okay, that's why you have plenty of marshmallows. I love that you use the bag.
I do this.
Don't break the spoon.
We're really far, right, guys? Yeah. I do this.
I can't believe how different everybody's looks. That's what's really fun. So what have you figured out so far?
We figured out that you need a longer handle. So we took this and we're putting popsicle sticks over here. So it keeps falling to the side. So try to make it flatter.
Okay. And have you started your trials yet? Because you want to make sure you make a note as to where you did the fulcrum in the distance. Give me 5. Give me 5. People in the reading corner, can you hear me? If you notice, I only had 5 trials, but I conveniently made the back of the paper blank. So if you want to do more than 5 trials to get it right into the cup, because it takes you more than 5, what should you do? More than 5. And where are you going to write your data down, John Paul?
The back.
The back of the first page. I left it blank for you for a reason. Continue. Yes, Owen.
To find out how to do it.
What should you figure out?
We take the spoon and we'll move it around.
Oh, let's do that.
So just the spoon you're moving.
Yeah, we're moving the spoon around the bag.
And why that choice?
I didn't know how it works best, but it apparently does.
All right, you want to try it out and see if you figure it out? Okay.
Oh, it's actually. If we tried to get it, it would be under that would.
Wait, hold on.
Okay,
If we go like this,
so wait,
okay, can I go? Trial 3. Nothing. Trial 3. 0.
Would it help if your group would do what some of the other groups do? You think that would help, or you did? And what did you notice?
That they were like using all the materials.
They were using all the materials, yeah.
So distance is 0
Slingshot, a catapult.
kind of.
What's your lever? What's your fulcrum in a slingshot?
The let's get back to the base of it.
So it matters where the base is to shoot your item with the elastic and the slingshot? Does the handle actually matter? So is that your fulcrum?
I got it.
Okay.
A lot.
Start doing it as you're talking. That might help.
It's right here. Distance. Wait, it's ceiling.
Yeah, the pencil's part of it, but I gave you a pencil in the bag. Can you use what? The yardstick is what you're measuring with, so no. Because if you use the yardstick, are you going to be able to measure?
Well,
No. Won't work.
I did
Well, if you think it's a good idea, you're not stealing, you're borrowing good creative thinking.
I'm the rejector. I have the biggest job of all. Yeah, and it makes it so that
So does it work?
not yet.
It's getting close?
Our third trial, the distance was
The ceiling? So, I have a question. Why is it going up instead of over?
because we're either putting too much force or it's aiming up. When I let go, it's aiming
You might have to either, what do you have to change then?
We might have to change the height of the fulcrum like this, so it's like more so it's more facing down. So that's why we do. Oh, that's perfect. Oh, that is perfect. But we have to go down. No, that doesn't count. Should I hold this one?
I like how you're all working together.
Aiden's working with us
Some
so
hair
hard.
card.
I'm working with my paper to reject you all.
And fire.
32 inches.
Alright, so that one passed.
Rachel, why don't you wait to mark it until you're done with your experiment? You know you have it.
Alright, just guys, I'm gonna do last
You getting close to the cup over here?
What we tried to do is we put it like this and I held it up
Yep.
and I launched it like that.
Oh.
Can you do that?
Did we tell you how to launch it? Has everybody in your group had a turn to launch?
Yeah.
All right, I like that.
Tom, it's your turn.
All right, everyone's getting a hair card. Don't label it until we're done with science because of your creative ingenuity.
Wait, is everyone getting a hair card?
Well, I gave 2 groups once. One for collaborative effort and one for creative ingenuity. What's collaborative effort? What's collaborate mean?
Collaborate means like use it.
Yeah, if you collaborate, and effort and work when you're working on it. So what would collaborative effort mean?
Effort together.
Yes, that's
Good teamwork.
that is exactly what collaborative effort means. Good teamwork.